Okay, you want to look at a problem. Let me point out one thing that I was speaking kind of flippantly and I was incorrect. That's not equal to 0. I said that was equal to 0 yesterday, and it's not. So I should have I should have not said that. I was looking over things. What?
The 4 makes absolutely no sense to me. Because I went through and actually did the commutator of h and x, and I got 0.
Well, if you do the commutator of, let's just, that's why I had this extra page. Okay. Commutator for h and x. The oh, p squared over 2m plus e0 cosine of, there's probably e out here too.
It's minus.
It all is meaningless in our work here. And does that have an x?
Yeah.
So we're doing this commutator, right? So we can quickly break it into two different commutators. And now x clearly commutes with itself. That means the commutator of x with x is 0. It cannot make any difference which one's which because they're the same. And so this here is 0, and I'm left with this side. So I have that. And then there's kind of a tricky thing to do to simplify your work. And I should have changed that to a to a parenthesis rather than the bracket, just so it didn't look like it was still a commutator. Now I'm writing this from memory, so I'm going to check to make sure that's correct. So if I expand out what I just wrote, so I'm going to put that in black. This is my check. So you see I have a minus and plus the same thing there. And so that is the same thing. So that black there is just to make sure that I had made the right substitution there to make life easy. Now, why does that make life easy? Because we have already determined what the commutator between p and x is. I'm just going to pull out the textbook because I don't want to make a mistake. XP is IH bar. And so if you do px, that's right. And so our commutator is equal to 1 over 2m times minus I h bar p hat minus I. Hey, wait. That is 0. No, it's 2. That's 2IH. Minus and a minus does not add to 0, it turns out. Right? Sure.
No, I had it all.
Okay, so I wanted to correct that misstatement, which is good that I did. Number 5, well, did you want to look at something else in the homework, or I wanted to look at number 5 as well? Just
Can you scroll down?
what?
I just want to be able to look at it later.
Okay. Okay, so let's look at the last one. The last one we have A operator is the second derivative with respect to B. And it asks us, is this Hermitian? We've already gone through and checked to see if X and I and ddx are Hermitian, right? We found they're Hermitian conjugates. And if it's Hermitian, it's equal to its Hermitian conjugate. And so how are we going to test this? It's basically that same thing to see if its Hermitian conjugate is equal to itself. And the way I did it in my solution, which I'm sure is not the only way, is I checked to see if this was true. And when you check to see if it's true, just like how did we do the example where we had ddx? When we were checking to see what its Hermitian conjugate was, what did we have to do? It was the one that required a little more work of the 3, right? I had to use integration by parts. Now, since this is a second derivative, what does that suggest you're going to do? You're going to do integration by parts twice. That's okay. So it requires 2 integration by parts, but we can do a logical thing to come to the conclusion that it's probably Hermitian. Because when I did ddx, what was its Hermitian conjugate? Negative ddx. So if I do another derivative, what's it likely to do? Switch back to positive, which would then make it the Hermitian conjugate is the same as the original.
So I'm still having a little trouble understanding, like the operator is equal to its own Hermitian conjugate. I'm just not understanding that concept because I know like you're doing the expectation value, so you can say that the expectation value is real and also the conjugate of the expectation value must be real. Mm-hmm. So they're equal to each other.
Yeah.
But the operator itself being equal to its Hermitian conjugate, could you explain that concept to me?
The reason, and the reason is buried in more math, is, well, there are only 2 ways to get real, to guarantee you're going to get real eigenvalue. And one of them is to have a Hermitian operator. And so that's why it had to be Hermitian operators, so that we're always going to get real eigenvalues. And that's a very skimming the surface reason on it. But that is the reason. And the other one, I just read something like 2 weeks ago. It was talking about, it turns out they don't have to be Hermitian. There's a special case, but we always, for quantum physics, say they have to be Hermitian. That was kind of a new thing. But there's a special area where you can have another kind of operator.
Okay, but that's just a property of the Hermitian
Yeah,
operator.
it's a property of it. Yeah.
Okay. Also, what you wrote up there, the FAG equals GAF.
Yeah.
Why wouldn't it be setting it equal to A being on the left side?
It's fundamentally the same thing. It comes out to be the same thing.
Okay, so
That was just the way that I did it in my solution. So
So you're just like taking the Hermitian conjugate of the entire thing so that it flips it
Yeah.
left, right? Okay.
All right, the last one. The first step, I'm just going to put a divider there, is to check that and show that it's Hermitian, and it is. Because otherwise we wouldn't do the rest of it. And so then we're going to say, okay, what are the eigenfunctions and eigenvalues? So now, insert yet another page. Oh, heck, let's make two. That way we'll have an extra maybe. So I want to find the eigenfunctions of this operator. So our basic equation that we had was A operator acting on function. This would be a function of x. Yeah, I'm going to put it the way I started. Equals A eigenvalue times function of x. Right, that's our fundamental definition. And so now I put that operator in, and so I have d second dx squared operating on function of x equals a function of x. And this is where our differential equations experience kicks in. And what is your differential equations experience? Very limited. It's limited to second derivative or first derivative, turns out. If you have something like this, the solution has that form. That's the limit of what I'm expecting from you. So given that form, then we put that into no longer a Schrodinger equation, but our equation finding function to this operator. And so what should I do from here? I'm going to pick on Aaron. What should I do from here?
So it would be d squared e to the bx, so just take the second derivative.
Okay, so taking the second derivative of this,
Which is b squared.
and so I have b, okay, so I did that in red. Well, that looks kind of simple, right? But it's correct. And so if A is my eigenvalue, then I'm going to have B is equal to the square root of A. And anytime I do a square root, what do I have to do? Plus or minus. So that means my actual function up to this point, now I better not use A. That's my solution up to this point. And the reason I say up to this point is what do we have to do next? This is not going from minus infinity to plus infinity. What does it tell us? You have a problem with that? Okay. Well, I guess I'll go back to the problem then. I was waiting for an answer. Okay. It says, and the solution is periodic, such that f of phi plus 2 pi equals f of phi. And so it's only defined over 0 to 2 pi, and then it repeats. So we don't have any has to go to 0 at infinity rule. Remember that was a rule we had before? Now we have that it has to repeat. So we have to have that's required. Well, is it possible for me to, okay, so with what I have written, what would f of 0 be? What's e to the 0? Okay, so I'd have b plus c on this side, and on the other side I'd have b e to the square root a times 2 pi plus c e to the minus square root a times 2 pi. How is that going to work out?
A has to be 0.
Okay, if a is 0, it does work out, but then we got nothing. It does work out. It works out if a is a negative value. If a is a negative value, I have a square root of a negative, and what does that give me? Yeah. And so what we have to say is, aha, only works if a is less than 0. So define k is equal to square root of minus a. So minus a is going to be a positive, and that's real. And my solution now becomes a sinusoid. And I wrote it as the sinusoidal form for the obvious reason. The obvious reason being, now if I go back to my condition, the periodic boundary condition is what this is called, that f of 0 equals f of 2 pi. Now I'm going to have, well, let's be a little more general. It didn't say f of 0 equals f of 2 pi. It said f of theta equals f of theta plus 2 pi. That's more general, and that's what the problem actually says. 0 and 2 pi was a specific case, but this is the general case. So I have d cosine of theta plus e sine of theta is equal to d cosine of theta plus 2 pi plus e sine of theta plus 2 pi. Well, oh, I forgot the k's. K, 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 K. Okay, the last K was saying okay. So I put all those K's in there. And of course, it probably would have been smarter for me to put just another bracket, a k outside or something. So how can this be true? True if and only if what's the periodicity of cosine and sine? 2 pi. So if k times 2 pi is an integer multiple of 2 pi, then we're going to be good. But if k times 2 pi is not an integer multiple of 2 pi, then it's not going to be the same. So k has to be an integer. And of course, it's going to be a positive integer based on the way we defined it. So if and only if k is a positive integer. So now we're pretty much done. We're going to have our function is, I can just put this d cosine kx plus e sine kx, where k is 1, 2, 3, etc. And then what are my eigenvalues? Okay, so you have an operator acts on a function, and it gives you an eigenvalue times the function. So with what we started with, energy was our eigenvalue. We had the Hamiltonian operator acting on the wave function gave us the energy times the wave function. So that's our operator and observable relationship. The eigenvalues are now the observables for a specific operator.
So we defined k as being square root of negative a. So then a would be negative k squared.
Bueno. So we had k has to be 1, 2, 3. So a would be minus 1 squared, minus 2 squared, minus 3 squared, and so on. So the definition, Chad, is right here. This is the eigensystem definition. Operator acting on eigenstate is equal to eigenvalue times eigenstate. So it's terminology, right? So we good?
So can you explain again the k2 pi thing? It'll only...
Yes. Because we have cosine of, it was k it was kx here. I used x. I should have used, actually, was it theta or phi? I used the wrong variable, let's be honest. I didn't use the variable defined in the problem. Yeah, it should have been phi. I used x where it should have been phi. And so our relationship that was required, our periodic relationship, that was our periodic boundary condition, or our relationship that had to be met. And so I have x here, but for x I put in theta instead of phi, and then theta plus 2 pi instead of phi plus 2 pi. But the k had to still be there because the k was multiplied by x or by phi. I can't believe I used the wrong variable all the way through the problem. I'm a little chagrined here. And so these k's are these k's here. And then I replaced the x with what was in parentheses there.
Mm-hmm. So, but the k, I get the k multiplied by the 2 pi, so
Okay.
you end up getting an integer multiple of 2 pi. But what about the k theta? How do you guarantee that when you add the k theta plus the k2 pi, that you're still getting an integer?
Because I had on this side k theta. So k theta plus anything that's an integer multiple of 2 pi is the same as k theta.
Oh, okay.
Right. So
Okay.
the key is that I had k theta on both. All right, let's change to, oh, I just saved that. Well, no, I didn't save it. I don't want to save that. I want to go to today's lecture, which I think is this one. No, it must be this one. Oh, goodness. These are my different. It's this one. All right. So this is where we left off last class period. Last class period, we had gone through and found the eigenstates for the momentum operator. And we had a little bit of a difficulty there because it wasn't normalizable. But we came up with that, as it says, this ersatz function that could kind of work for us. We're moving forward from there. So we learned before that if we have a complete, our solution, our eigenstates now, I'll say, if our wave functions are complete, they span all space, then I can write, as Dirichlet said, any function as a linear combination of those different eigenstates. And so this here is that statement that any function f of x, that subscript 0 means time, or that not subscript, but that 0 in there means at time 0 because we're taking the time independent, is equal to the sum over all of my eigenstates times some constant, where that constant is found by the equation shown above. So it's like, 0.3 psi 1 plus 0.1 psi 2 plus 0.4 psi 3 and so on. So we've already seen that. Now we're going to go a step further and say, okay, we can use the same idea to transform between momentum and position space. What does position space mean?
Isn't that what we've been working with?
That's what we're working with. That's where our variable is x. That's what position space means. So our variable being x mean its position is what we're working with. That's all the space I'm used to using, right? Anytime I talk about space, I mean position space. But in mathematics and physics, we can talk about other spaces. So you can talk about momentum space, which means I have my particle and I have a wave function in terms of momentum, and the psi mod squared gives the ability to be a specific instead of the probability of being in a specific location. And so this is a transformation, and it essentially is a Fourier transform. And you'll see here we have the function that we have just, oh boy, highlighting does not work when you have equations. Getting rid of highlighting also apparently is an act of God. Okay, it's all but one little line gone. So this here should look pretty familiar, right? And then with that quasi-normalization constant out front. And so how we transform between a momentum space and a position space wave function is shown here. So this is the momentum space wave function. And here's the position space. And there's no way to make this more real than to do a stinking problem. So that's what we're going to do. I brought my textbook, so I have, a cheat sheet to guide me as I go through this stupid thing. I say this stupid thing. It's not stupid. Problems can't be stupid. Only people who do them can be stupid. As I bumble my way through a problem. So here's the problem. A particle of mass m is bound in the delta function well v as a function of x. It's equal to minus alpha, and that's dx. That's supposed to be a delta function. I don't know how I got that wrong. Delta function x, right? It says delta function, then it has d. We've already done this problem. We're not redoing the problem. What is the probability that a measurement of momentum would yield a value greater than P0 equals M alpha over H bar? Or, wow. I'm pretty sure those are supposed to be there. Now this is, like I said, it's a problem from the textbook. Actually, is the last one also? No, okay, good. I was afraid the last one was as well, and I was going to feel dumb. It says example 3.4 there, so let me just find example 3.4 in the textbook so we can follow along. And in fact, no, I was going to give you the textbook and let you give me. First, I have to find the example. There it is. Yes, my corrections were both correct. Okay, so our starting point is those are the solutions that we've already found. So we're not going back and redoing a problem. We're just going to go forward from there. And so the first question is, how do I find, going back to the highlighter, the probability that a measurement of momentum is greater than something? How do I find that? Let's go back long time ago, the way back machine. If I wanted to find the probability of a particle being between A and B in position space, how did I do that? Yeah. I did that. That was the probability of being between A and B in position space. Now I want to do the probability of momentum greater than momentum zero. So that should be the integral. What should my lower limit be? P0. My upper limit, infinity, because it's just greater than P0. But then I need to have the momentum space dp, right? Because I want to find the probability of being above p, I'm going to have a momentum space function. That's why this problem is here, by the way, is so that we have to transform from position space to momentum space and then do the integral. So we have our position space solution already. So I don't care about the time aspect. I just don't care about it. It shouldn't matter in time. How do I find my momentum space conversion of that? Okay, I'm going to stop at that. What comes next?
Integral from, I guess, P0 to infinity. Or do you have to do it all the way from negative infinity?
Minus infinity to plus infinity. We're doing this right here. So minus infinity plus infinity of negative IPX. E to the minus IPX over H bar. And I'm integrating the X out of it. So here's the full equation, just because my handwriting's not as easy to read. And so now I have to actually do that. And now I have to put in my psi, so I have square root of m alpha over h bar. E to the minus m alpha over h bar squared times absolute value of x, then E. So I have this integral. Now, you don't have your textbooks out. Let me quote from the textbook. The momentum space wave function is therefore, and he has the integral rewrote, and then he has equals square root of 2 over pi. Oh, wait. Yeah, I looked at the next line by accident. I was like, that didn't. P0 to the 3 halves, e to the minus I e t over h bar, all over p squared plus p0 squared. And continuing to read, parenthesis, I looked up the integral, in parentheses. In other words, okay, so that's not going to be just simple and straightforward. In previous years, I've actually gone through all of the joy of doing that integral. Note that P0 just appears here. And you're like, but P0 hasn't, P0 was defined as this. So any place that M alpha over H bar occurred, he substituted P0. So for instance, right here, that was square root of P0. Let me change to a non-permanent. Oh, that's the wrong one. Well, this one will work. This here, that was square root of P0. This here, that was P0 over H bar. So that's where the P0s came from. It's not like it was some magic thing that appeared. So that's how he finds the function. Now that we have the function, our next step, gave myself one page. Our next step is to integrate that from P0 to infinity. And guess what he says there? I looked this one up too. So when he did this integral, right, it's just integrating this from P0 to infinity and then plugging in numbers. It turns out to give you 0.0908. It's 1/4 minus 1 over 2 pi is what you get when you do that integral. So I'm not going to do that integral. I mean, it's all I would have to do is rewrite this with an integral sign in front of it that's going from P0 to infinity, and then say, now looking this integral up, it gives us this. And like I said, I've done it in the past, but it takes a lot of time to do that calculus. And it gives you practice with calculus, but it's not a special quantum learning experience. So let's move into the generalized uncertainty principle. Tell me what the uncertainty principle is.
So like H bar 2 is, can't remember if it's which side. And it's like greater than or equal to the standard deviation of momentum and position.
Perfect. Went perfectly from right to left in the equation. So that's our uncertainty principle. Generalized uncertainty principle. We're going to find where it really comes from here. Right? We've already seen the example of with a Gaussian distribution, I said that gives you the minimum uncertainty, blah, 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 blah. So now we're going to see an actual derivation for the uncertainty principle that gives it clear as the muddled math can be. So we start with, let's just take the definition, uncertainty, which is the standard deviation, which is what Chad said, is related to expectation values by this relationship. The uncertainty squared is the expectation value of the operator squared minus the expectation of the operator quantity squared. And on the right-hand side, it's just showing how you calculate that using Dirac notation. You can probably see how the expectation value fits in with Dirac notation now, don't you? The only difference between this and this is that you don't show the size or that line. So if we define a new vector, and this here is all a long scheme to make it quasi-clear. I say quasi-clear because it's got a lot of stuff right now. So if we define a new vector f that is equal to the A operator minus the expectation value of A acting on psi, that's fine. Expectation value, that's just a number when you get down to it. So that's, an operator minus a number is certainly a valid operator. Then if we take f acting on f, what should we get? If f was normalized, we'd get 1. But f is not necessarily normalized, so we go through this, and we have this stuff here in psi, and then that stuff there with psi again. And then we collapse into a whole bunch of separate terms. So we take the A operator psi gives us this term. Then we have A operator, let's see. Well, I think the second one that was done was the minus A expectation value and then A operator. So minus A expectation value, that's just a number, so it's brought outside. And then the psi, A operator psi. And so following that order, since I'm the one who actually did this, it probably is following the order I would always use. Then the next one in order is taking that one, that one. They this here. Wait, no, we did that one. Crap. Well, you're just taking the 4 terms. You just got to brute force your way through. And so you have 2 cross terms. These are the cross terms. And then these are the second terms in each one. This is the first term in each one. So this one here is taking this. That's fundamentally the only one I didn't explain. But if you look at these, I'm sorry I've made so many marks. What is this always equal to? That's 1, because my psi has to be normalized. So that's 1. And what is this going to be? Well, it's the expectation value of A. Right, just like right here. And what about this here? Yeah, you could put a star somewhere there, but it's real, so it's still just A. And so we have, and then this, let's see. It seems to me I'm a 2 off here. this one here is the one that I am thinking about now. A operator psi, A operator psi. Oh, yeah, that's going to be, because A operator psi, A operator psi, you can do the Hermitian conjugate and move the A operator move the two together, and that's A squared. And so we have two of these A squareds and minus two of these expectation value of A quantity squared. Only thing that's wrong with my math here is a factor of 2, right? Because there's 2 of each. I should have had a 2 out front. I'm not sure how that got past me. So does that ring true?
Yes.
Okay, chat says yes. Aaron is still thinking about it.
Have not gotten there.
Okay, well, so you understand where these terms came from right here, right?
Yeah.
And then if we take those terms and we evaluate them, this one here can be rewritten as you take the Hermitian conjugate when you move it from one position to the other.
Oh,
But
yeah.
if it's a Hermitian operator, the Hermitian conjugate is the same thing.
Yeah, I get how you got
Okay.
the last row, but I thought you were asking if it makes fundamental sense.
Oh, if it makes fun. No, we have, okay. Yeah, that's, I wanted to make sure you saw how we have gotten to where we have here. So we define another variable just the same, and you're like, well, why'd you do that? Well, the reason to do that is using the Schwartz inequality. I'm still off by the factors of 2, and I'm not sure why, but I mean, it's pretty clear that I have 2 of these and 2 of these, right? Pretty obvious. And so there's got to be a 2 there.
But you have, that first one was A squared, the expectation value of A squared, and the last one is expectation value A.
Oh, okay, right. It is all correct. You're correct. I was not paying attention. So this is expectation value of A squared, and then this is A expectation value of A quantity squared, and these are minus 2 of the same thing. Okay, so there is no mistake. Good. So there I've substituted what each one is up above. And so minus, minus, plus, that's how you get just 1 and 1. I'm glad we didn't go too far there. Well, unfortunately, now we're out of time. I'll have to pick up here tomorrow because we're not going to be able to make any sense of it. Tomorrow? No,
next
Monday.
Can you be sure to post this video by this evening?